if you haven't done complex numbers yet, I wouldn't go to this straight away. But I would imagine that the people would have done complex numbers by this stage before they go to induction. So how this works is just standard induction, but we're going to be using a lot of compound angles. So a couple of things. So we're going to need complex numbers, because otherwise you might be confused why this I is here and why the whole thing works, as well as compound angles. So those are the two things that we're going to need for this proof. So it very much follows the standard inductive proof. So we're going to let n equal to 1 because this works for n greater than or equal to 1. We're going to have cos theta plus I sine theta to the power of 1 is cos of 1 theta plus I sine of 1 theta. So we're going to just have cos theta plus I sine theta is cos theta plus I sine theta, which is clearly true. So therefore true for n equals 1. Okay. We're going to have n equals k for k greater than or equal to 1. So we're going to assume that cos of theta plus I sine of theta to the power of k is cosine of k theta plus I sine of k theta. Okie doke. So we're now going to have n equals to k plus 1. Therefore, we're going to have cosine theta plus I sine theta to the power of k plus 1. Again, we want this to be cosine of k plus 1 times theta plus I sine of k plus 1 times theta. So again, using powers or power rules, we're going to break this down to cos theta plus I sine theta to the power of k times cos theta plus I sine theta. So again, this cos theta plus I sine theta to the power of k, I'm going to mark in this highlighter. And we're going to relate this to this inductive step. Slight OCD, I want it all filled in. So those things are going to be linked. And so we're going to have cosine of k theta plus I sine of k theta multiplying with cos theta plus I sine theta. When we expand this out, we get cosine k theta plus, or cosine k theta cosine theta plus cosine of k theta I sine theta plus I sine k theta cos theta. Now the i's get -1, so we're going to have minus sine k theta sine theta. Okay, so we're going to group the real and imaginary. So if we have the reals, and we're going to have the complex. So the reals are going to be cosine k theta cosine theta minus sine k theta sine theta. And the complex numbers, we're going to have I times cosine k theta sine theta plus sine k theta cosine theta. Now, from the double angle formulae, if we let A equal k theta and B equal theta, we can see that it's cos A cos B minus sine A sine B, which is cos of A plus B. So cos of A plus B, so k theta plus theta. Similarly, again, we're going to let A equal to k theta and B equal to theta. Again, here we're going to have sine or cos A sine B plus sine B cos A, which is sine of k theta plus theta. So combining this together, we get cos theta plus I sine theta to the power of k is cosine of, now factoring a theta out, we get k plus 1 theta plus I sine of k plus 1 times theta, which is exactly what we wanted. So again, therefore true for n equals 1, and assuming true for n equals k proves true for n equals k plus 1, therefore true for all n greater than or equal to 1, and that's the proof.